I'm 15 years old, secondary 3 for Ennis High School. In this lesson, we'll continue with another lesson of hydrogen spectrum series. So a quick recap from quite a long time back, where we had different stuff like Rydberg's empirical formula. So for now, we will be again recapping what we had before, alright? So Rydberg's empirical formula, what does it look like? So for Rydberg's empirical formula, you have 1 over lambda, and this is equal to your Rydberg's constant, 1 over n1 square minus 1 over n2 square. So this is what it looks like. Now, what is so special, or what does each of these even mean? So lambda is your wavelength. But wavelength of what? So these, since the series is for hydrogen spectrum. Now hydrogen spectrum, that means you only have for hydrogen atoms. Well, hydrogen atoms, you just have a proton and an electron, alright? So what's so special about a proton and an electron? Now, in this atom, when you have the proton and the electron, you can give the electron energy to make it to excite it, so that it can jump from one shell to another. Or once it gets de-excited, it releases this light, this energy as light, and goes back into its previous shells, depending on how much energy it lost. So that wavelength is of this light that is given out. So this Rydberg's constant is what we can find out later. Then n1 and n2 are your so-called quantum numbers. Well, it is pretty much which shell number it has, where you have other different calculations to find out exactly what the values of n1 and n2 are, alright? So we will again be showing how this is derived. Of course, since this is a Rydberg's empirical formula, that means Rydberg at first discovered it by doing experiments, since it's an empirical formula, but we will only be theoretically showing how you can get this formula, alright? So to show this, you would need a combination of both classical physics and modern physics. But modern physics, all you would need is some of the things from Einstein, stuff excluding your relativity and all. So later on you'll see what exactly do we need. To be more specific, quantum, alright? So you will see what kind of quantum things we will need later. Alright, so let's get started. Now when you think of classical physics, who would you first think of? Of course, for many of you who just began to learn physics, you would be thinking of Newton, right? Since you have the apple that fell onto his head and then he discovered gravitation and all. So of course, Newton would actually play an important part here. But would there be any other person you can think of? Now, if you think of it as your hydrogen atom, where you have a positive charge and a negative charge, which are your proton and your electron. Now, think of these charges. Who would you think of? So, they will definitely have that kind of electrostatic force between, right? Which would lead you to think of Coulomb. So, starting off, we would be using the Coulomb's law and the Newton's law, right? So, Coulomb's law. What is so special about Coulomb's law? What would we need from Coulomb's law? So, from Coulomb's law, since this is your electrostatic force between your two charges, that means you would have F is equal to 1 over 4 pi epsilon naught Q1 Q2 over R square. Alright, so this is your Coulomb's law. And now, your Newton's second law. Which is of course simply F equals ma. But you would need to find a relationship between these two, right? Now, how do you find a relation between these two? You have to be aware, since this is in an atom, which means the electron is doing circular motion around your nucleus, or in this case, just a proton, or a positive charge. So since this is between the two charges, can you think of anything to find its so-called radius, alright? So then you can combine Newton's second law with your circular motion. So what kind of acceleration would you be taking a look at if it is in the radial direction? Well, that means there can only be one thing, which is your centripetal acceleration. And how do you calculate that? That would be, so you would have v square over r, alright? So since both of these are along your radial direction, that means they are equal. So this is just the force between the proton and the electron, while this is your centripetal acceleration in this circular motion that you have, right? So that means you can equate both of these, where you have 1 over 4 pi epsilon naught. I'll just shorten this part a little bit. So Q1, Q2 over r square is equal to mv square over r. Then you can find what r is. So for r, you would just move it around a little bit, but of course then you can also change the Q1 and Q2. Now why is it that you can change Q1 and Q2? Because you have to be aware, we're doing for hydrogen atom. Hydrogen atom, it's either one is a positive charge, which is your proton, a singular proton, and the other is a singular electron. So that means both of these would have a magnitude of E, and so technically if you're just saying magnitude, it's technically E, but since this is an attraction, that means the negative from electron would have to cancel out with the attraction, which already has a negative. So this is a positive E square, alright? So for this part, then you can kind of work this out. E square over 4 pi epsilon naught mv square. Alright, so this is your r. Well, of course, you can also choose to calculate out what this r is, since it is just a charge of the amount of charge of a proton or of an electron, but you have to be aware for electron it is negative. Then pi is obvious, it is your 3.1415. Epsilon naught, which is your permittivity. Then m, which then you can find out your mass of, so you have to be aware, mass of what? In this case, it is the mass of an electron, since it is an electron moving around your proton. So v, then you would have to find out exactly how fast this electron would be moving in a circular motion, alright? So when you solve this out, that would be your, so what do you think this would be if you could find it out? Well, then you realize, how do we find v? It doesn't seem very possible, isn't it? But along with that, there are a few other problems, which we will solve later, don't worry about it. Even though you may not know what v is, there are other ways to find it, alright? So, what are some other problems that come with classical physics? Alright, so you have to be aware, this part is actually where we end the classical physics part. Right, so a few problems. So when we think about this hydrogen atom, of course, we couldn't find a V, right? Unless you can somehow detect its value, which I'm not sure how you're going to, but now we're not sure of what that V is. So that means we cannot determine its radius. So what is what is its radius? This radius, we have no idea. Now, why does it emit light? Here, it is not explained either. So, other than why does it emit light, there are also problems like, so after it emits the light, how many photons will be there, alright? So there are also more advanced problems about stuff like your decay and all, but those we will discuss more about them in the future, alright? So for beginners, these are some of the problems you can think of. Well, of course, if you know of some other problems, those will be great. You can think about it on your own first. But of course, later on, or in other lessons, we would be explaining more about how these problems get solved in later stages of physics, or more specifically, more in modern physics, alright? Since this is just the classical part. Right, so we have these problems in mind. How are we going to solve them? So, of course, moving on to modern physics. Now think about it again, modern physics. Who would probably be the first scientist you would be thinking of? Well, if you just started learning these, then it would probably be someone like Einstein, since he's so famous, and for his entire theory of relativity, photoelectric effect and all. But we are not going to talk about those here. Yes, we will be using Einstein later, but those will be for something different. So starting off, it would actually be with Bohr. Okay? So starting off with Bohr, we would have his assumption. So what is so special about his assumption? Now, if you can recall what I talked about later, something about quantum, okay? So this would be a quantization of angular momentum. You might be wondering, wait, how does angular momentum come into play here? You might be very confused at first. But essentially, you can consider angular momentum. Think about the electron doing circular motion around your proton. So that electron, you would have its angular momentum. So how do you find angular momentum? NVR. So here, what kind of assumption he made was that this has to be n, where you have this quantum number that you have, okay? So quantum number, well, of course, it will just come in like integers, if you can think of it like that, which is why this is a quantization, alright? So this part, it could be very difficult to understand, but of course, we would explain more about why you can have all of these in the future, alright? So here, you have two ways of writing it. It is either h bar, which you can say it is the reduced Planck's constant, or the Dirac's constant, depending on how you like to say it more. Or you could change this reduced Planck's constant, So there is a Planck's constant, which is the reduced Planck's constant is just a Planck's constant divided by 2 pi. So that's it. Alright, now it might seem quite weird how to relate these two again, but how about let's express R in terms of all the others again, which you would have R is equal to NH over 2 pi mv. Now since we didn't know what V was, right? How about let's try to find V for this part. Is it right to do so? Alright, So since both of these are now in R, you can, now there are a few possibilities. It's either you could try to use V here, or alternatively you could just equate the two together. So when you equate these two together, what do you think you will have? Or even in another way, you can also find V in terms of all the others and then sub it into here. So it all depends on how you like to do it. So those are just some of the possible ways that you can think about it. But then when you realize that if you just equate these two, again, you will just be finding V. So might as well just find V from this part, alright? So V, it will be NH over 2 pi mr. So now you can substitute this part into what we had, which will give us R is equal to E square over 4 pi epsilon naught m and h over 2 pi mr, and this entire thing squared. So what does this give us? This would give us, so you would have no more force, E square still stays, and you have a R square. There would also be a pi. So this is the form that you will be left with. So now does this look solvable? Now you have pi, which is a constant, E, which is a constant, m, your mass of electron, which is a constant, your radius, radius to find radius, how about let's change that up a little bit, R. So this will be epsilon naught n square h square over pi E square m. Alright, does this look better now? So, of course, the entire denominator is a constant, your permittivity is a constant, this depending on the shell is a constant, and of course, Planck's constant is definitely a constant. So that means this, you can find it out to find your, Bohr's radius for hydrogen atom. Alright, so of course you can go ahead and use your calculators to find out what this part is, except you just have to know what each of these constants are. Alright, so the result you get in meters, or depending on how you converted it, it would be your Bohr's radius for hydrogen atom. Alright, so what else would we need from this part? Does it seem like we need anything else? So now you might want to change your V in terms of all those constants while you're at it. Now why do you need it? So later you will see why, alright? So V is equal to NH over 2 pi m epsilon naught n square h square over pi e square m. So you can simplify this part once again. So NH is cancelled out with the part below. And does this seem right for what you're going to have? Alright, yep, it does seem right. So this is the V that you're going to get. Now I'm going to show you why you would need this part. So now, let's say you were to calculate mechanical energy. How are you going to calculate it? you are going to calculate mechanical energy with potential energy and kinetic energy, right? Yes, you are going to need both of them to find your mechanical energy. So how do you find each of them? Well, for your potential energy, what you are going to have is your Coulomb's law again, which you are going to see negative 1 over, well, negative again because of your attraction. So 1 over 4 pi epsilon naught, and you're going to have E square over R. So R as, well, this is potential energy. And then your kinetic energy, which is half mv square. Now that is where your v comes into use. So half mv square. Half mv, so this part. Well, of course, at the same time, you could also change your r into your different form that you would have, which is epsilon naught and square h square over pi e square m. Alright, so I guess this is what you're going to see now. So you would try to simplify both sides a little bit. Pi is gone, negative e to the power of 4 epsilon naught squared n squared h squared m. Or for the other parts, you have over 8 epsilon naught squared n squared h squared m e to the power of 4. So then you would realize the parts without your, well, how do I say this? Like, you realize that you can combine both of your fractions to get negative m e to the power of 4, 8 epsilon naught squared n squared h squared. So this is what you're going to get for your mechanical energy. Wait, why are we calculating mechanical energy again? Alright, you'll see that later. But then you might again wonder, wait, potential energy, you're using electrostatic? Well, yes, of course you can. So with this mechanical energy, we can then move into the next part of what we are going to have. So when I talked about Einstein earlier, this is actually where he would come into play. But he's not alone. Well, can you guess why? So although we can say that this is Einstein's assumption, you have to be aware. Okay, so Bohr, he used quantization of angular momentum. Now what did Einstein use? So Einstein actually used the Planck-Einstein relation. Alright? So the Planck-Einstein relation. Wait, Planck again. We had a Planck's constant and now he's here again. So Planck-Einstein relation. Now what is this exactly about? So let's just say, since this here for hydrogen atom and its electron, it jumps from shell to shell, sometimes increasing its shell, sometimes decreasing. So that means there would be a change. So what exactly is this change going to be? Now, if you want its increase, that means you would have E2 minus E1, right? So then what's so special about this? So E2 minus E1. Now that is where you have this Planck-Einstein relation. So this here, it becomes, you can write it as H nu. You can write it as H nu, or you can write it as HF. Or you can also write it as HC. So what do you think this part would be? over lambda. Alright? So this is what you're going to see over here. Now if you're wondering why would this be c over lambda, you can think about it. Since nu is actually a frequency, which why you can also write it as f. C is your speed of light. Lambda would be your wavelength. But then h, Planck's constant, comes into play here again, right? So now what's so special about this part? So since we need 1 over lambda, that means we can find 1 over lambda. So 1 over lambda is equal to E2 minus E1 over HC. Alright? So now what does this have to do with us again? Now we calculated mechanical energy for a reason, which is where we're going to use it right now. So E2 and E1, we would be using your mechanical energy to find them. So mechanical energy, now for E2, that means you have N2, which is negative m e to the power of 4 over 8 epsilon naught squared n2 squared h cube c. And then negative, but you have to have another negative to make it plus. So here you add on m e to the power of 4 over 8 epsilon naught square n1 square h cube c. Alright, so then you will just combine these two parts, taking out the constants that you can, which is m e to the power of 4 over 8 epsilon naught squared h cube c, and the rest inside will be 1 over n1 square minus 1 over n2 squared, which the rest of these parts, surprisingly a huge chunk of them, it would just be your Rydberg's constant. So here we have shown where your Rydberg, so here we have actually shown that your Rydberg's empirical formula actually works. Even though he only deduced it from an experiment, it is actually very true. So this is where we combine your classic physics and modern physics. From classic physics, you have used Coulomb's law and Newton's second law. While for modern physics, you have used, you can say it is both Bohr and Einstein's assumption, or it is the quantization of angular momentum by Bohr, and your usage of Planck-Einstein relation by, well, you can say it's by Einstein, but you could also say Planck actually had a large contribution to this, since the Planck's constant is just everywhere. Alright, so I hope for this lesson of showing how you can derive the Rydberg's empirical formula theoretically has helped a lot. Alright, so I'll just be ending this lesson here, and thank you for your watching.